All right, I'd like to thank the organizers for inviting me here. And I'm either here as the provocateur to give you some food for thought, or as the comic relief, and I don't really know which. As you can see, I have grown my hair out because I am John Hayes at Penn State. I am not Matt Hayes at Penn. So I grew my hair out so that you can tell us apart. So I'm a sensory scientist. What does that mean? So for 5 decades, the discipline of sensory science, which has existed since the 1940s, has been defined as the scientific discipline used to evoke, measure, analyze, and interpret responses to products that are perceived by the senses. Or more simply put, I'm a psychophysicist, and I know that's a big word, but I'm an experimental psychologist that studies flavor perception and how to measure it. Or even more simply, I like to study when you reformulate a food, can people tell, and do they care? Those are the 2 motivating questions in my lab. And so we do this with large blind taste tests. So we use large numbers of people, we democratize taste, we bring people into the lab, we do blind taste tests with little sensory booths, so we're getting independent evaluations, so they're not influencing each other, so we're not measuring social facilitation. And we're very, very fussy about spending how we manage our stimulus control. So for example, in this project we did for the peach growers, we had 4 different kinds of peaches. They wanted to know which peach variety people liked the most. Some were clingstone, some were freestone, but we wanted to reduce all those variables. So we had these poor students cutting every peach down to 1 centimeter cubes so that we could completely blind even the skin color of the peach and whether it was a freestone or a clingstone peach. So really, we're trying to figure out how to make food more delicious. And one of the ways we can do this is by leveraging these tools of sensory science and reformulation to try and deliver foods that are more healthful and help people achieve their dietary goals while still being delicious. And so this is a project that we completed a couple years ago with a big collaborative team. And so what happened was the first step of this project was to actually use NHANES data and figure out what foods were most commonly eaten by Americans. Our team did not do that. Then what happened was a research chef went and reviewed those for feasibility. So Rachel Gooding, the research chef on this project, she went and she tried to figure out which ones of these foods she thought she could actually meaningfully change without really negatively impacting acceptability. And so then she reformulated. And so you can see across these 10 different foods, we took salt, sugar, and fat out of each of these, but we didn't just go for a simple 20% reduction of each because different foods require different strategies. So we didn't use a one-size-fits-all approach. And then my team came along and we validated these in blind taste tests. So we tested 1,000 people in the lab, actually 973 people in the lab, for all these different foods. And so you can see the mean age was usually in the 40s, so these are not university undergraduates. These were drawn from our participant pool that we maintain in my research lab to do product testing. And you can see that, as you always expect, wide range in age, but the gender balance was skewed towards women, but we did have both men and women in our sample. And so when we do that, here's one example of meatloaf. So you can see the original formulation is the orange one, the OG sample here. And then when we go and make it healthier, it's nutritionally improved. What we find is in a blind taste test, that one is liked less. Okay, so when we take the salt, sugar, and fat out, people like it less. However, if we compare it to the flavor-enhanced, nutritionally improved product, the one where herbs and spices have been added back to the product to deal with the fact that salt, sugar, and fat have been removed, what we can find is we actually find no difference between the OG, the original one. So we actually see that we can rescue the acceptability of this after we've taken the salt, sugar, and fat out by using herbs and spices. And in fact, we did this across 10 different foods. And you'll see in 2 of those foods, the flavor-enhanced nutritional infusion was actually better than the control. We actually made it even better. And then for 5 more of these, what we actually found is we were able to at least achieve parity. We were able to rescue that consumer acceptability in a blind taste test. And unfortunately, in 3 of the foods, it didn't work. It didn't work at all. And this makes perfect sense in hindsight because as soon as I looked at these data, I thought, oh, this makes perfect sense. If I take cheese pizza and I use no fat mozzarella, and now I have a rubbery piece of pizza, no amount of oregano on the planet can save a rubbery slice of pizza. Okay, so this makes perfect sense. So this is just one example about how we can use sensory science tools to help people reduce the reduction of foods that are high in salt, sugar, and fat. But more fundamentally, and this is the big story that I want to tell you today, there's an implicit causal chain that links food formulation through health consequences. So we can think about the food formulation as the stimulus concentration. We can then think about that causes some sensation, or when I say sensation, you could also just think that's the flavor of the food, that's the taste of the food, to the question that was asked earlier. And then we can measure how much pleasure we get from that food. Then we can measure whether or not people eat the food, how often they pick it, how much they eat it. So all those different factors. And then in some cases, people also even try and link this through to consequences of use. I will not do that today. So that first connection is really just a classic psychophysical question. It's a dose-response function. So here are some data where I'm showing you this relationship. And so what we see here on the x-axis is increasing sucrose concentration, and on the y-axis we have an increasing fat concentration. So this is a factorial design where you're mixing everything from skim milk all the way up through heavy cream with 0%, 5%, 10%, and 20% sucrose. So it's a very classic design that Adam Janowski used back in the 1980s. Then we can fit a response surface model to this to show that, lo and behold, as sucrose goes up, sweetness goes up. Not exactly surprising. But the one thing that I want to highlight here is when we use a response surface model, for those of you that are hikers, this looks very much like a topographic map. So if you think about going for a hike and you decide what that path is, when you're crossing lines, you're actually hiking uphill. And when you're moving along the line, you're walking along that ridge. So keep that in mind. We can do the same thing with creaminess. And what we can see there is, for the most part, as you increase fat level, creaminess goes up. But we can also see there actually is a little bit of viscosity coming from that really high percent sucrose. 20% sucrose is quite viscous, so you're actually getting a little bit of creaminess, a little bit of mouthfeel from that, which is why those lines are not perfectly parallel. So that's one way we can model this relationship. But we can also jump right over sensation and ignore sensation, which is often what the food industry does. They just go straight from, if you think like a chemical engineer where you're just trying to process optimize something, you're going to go straight from the formulation all the way through to the outcome variable, in this case, pleasure. And what we can see is we can come up with a response surface here where we get this classic bullseye plot, and we can see that the optimal liking occurs at a very specific concentration that's the result of the interaction of those ingredients. And I also just want to point out that these data were presented at my very first SIB in 2006 when I was a PhD student. So I want to take you on a brief thought experiment. This is the Drake equation. So Frank Drake in 1961 was first working on search for aliens, right? And he was trying to figure out what's the probability that we can actually find aliens in the universe. And so N over there on the left is the number of civilizations that we might be able to talk to. And then all the other variables are rate of star formation, fraction of stars with planets, number of planets that could support life, planets that do evolve life, ones that get intelligent life, not just life, ones that develop radios, and ones that are still alive for us to listen to. And you can plug a bunch of reasonable estimates into all of those, this thought experiment, and you can come up with a probability of what that number of civilizations we could detect. And I realized we could do the exact same thing with our implicit causal chain. So we can say, what's the effect size linking each of these chains from proximal to distal along this presumed causal chain? And so I was lazy and I went to the literature, but I went to my own literature first because I know my own literature better. And so here's an example of a study we did about 10 years ago. For those of you that have never been to Rhode Island or Eastern Massachusetts, there's a beverage there called coffee milk. This is not an iced coffee. This is not a latte. This is essentially chocolate milk, but it's coffee flavored. You buy the Autocrat coffee syrup, and the one Rhode Islander in the room from Little Rhodey is laughing because she knows exactly what I'm talking about. And you pour this into the milk, and then you drink it just like you would drink chocolate milk. And so we actually formulated that we made 20 different formulations of this in our pilot plant, and then we recruited over 300 people into the lab, and we did a fractional factorial design so that people weren't overburdened, and we measured both all these things in terms of formulation, but then we also measured sensation from all of these people. And we did things like we included blind replicates. That's why Formula 3 and Formula 19 are listed on the same line. They're actually the same formulation as blind replicates, which allows us in that design of experiment to actually fit these data quite nicely. So when I go and I do that, I can instead look and ask the more fundamental question, back to my Drake equation question of what's the relationship between sensation and concentration? And when I do that, I can see that sweetness goes up as a function of sucrose in that top left panel, not particularly surprising. But we also see that sweetness goes down as I add more coffee milk. So this is an example of mixture suppression that's coming from the bitterness of that coffee milk. So bitterness actually pushes sweetness down. And then we can see that milk itself has lactose in it. So more milk in the formulation also makes it sweeter. And then we see the same thing for coffee flavor on the bottom. So in multiple regression, I can show that I can explain 94% of the variance in the sweetness based on the milk concentration, the coffee extract concentration, and the sucrose concentration. Likewise, for coffee flavor, I can explain 96% of the variance, and this actually is clear in other papers that use the same sort of models. So this is very robust, finding that about 90% is a reasonable estimate here. So the psychophysical relationship here is quite strong, even when you use real consumers off the street. Then we can ask the question of what the relationship is between sensation and pleasure. And so this is a psychohedonic model. So if I actually don't try and link stimulus concentration to liking, but instead link the sensation to the liking, I can explain 63% of the variance in liking. And notably, this is a much stronger predictive relationship than that blue relationship if I try and go from concentration to pleasure. So in other words, by including sensation in the model, I can get a better fit and I can predict more. And lo and behold, we've seen the same thing previously. In that same data that I presented at my very first SIB in 2006, we see the same relationship, that the psychohedonic relationship is stronger than the other one. Then we can ask the question about what the relationship is between pleasure and use, or liking and intake. And so this is an incredibly robust finding. I was one time having dinner with Howard Schutz, and he asked me about what I was working on, and I told him we were trying to predict food intake as a function of food liking, and he said, oh, I did that in 1957, and I looked, and he had. And so sometimes you should talk to old people and have dinner with them. And so this is an incredibly robust finding that's been shown across continents, across lab groups over and over and over again. However, there's an incredible nuance here that many people have overlooked, and I'll come back to that, but this relationship is heteroscedastic. So we'll put a pin in that for that moment. I'm not going to explain that right now because I want to land the plane on my Drake equation story first. So to land the plane here on our thought experiment, if we look at each one of these possible connections, if we assume that the first to second variable is 0.97, the second to third variable is 0.8, and then the third variable is to fourth variable is 0.6, we have an attenuated correlation. The highest possible correlation we could ever see is about 0.5. Now let's be a little more conservative and pick slightly lower numbers from each of those. And that maximal possible correlation drops even more. And then if I drop a little bit more, the maximal possible correlation you could ever imagine to see is 0.12. Or in other words, that at best formulation could maybe explain 22 to 2% of variation. So this idea that it's all about the formulation, this doesn't make any sense. We already know this, that food choice and food intake is driven by access, economics, childhood, feeding parents, parental modeling, all the other factors that we predict. So when we spend all this time worrying about formulation, we're ignoring all those other things that drive food intake. Okay, so I told you I would tell you what heteroscedastic meant. So if you go to statsmakemecry.com, you get a really nice definition, which it says that heteroscedasticity is a hard word to pronounce, but it doesn't need to be hard to understand. Simply put, it means that the variance is not evenly distributed across the entire range. So what you can see is over on that plot, you can see I have a lot of variability on the right-hand side and very little variability on the left-hand side. And critically, this is exactly what we see in the food liking relationship. And get your cameras out. You have my explicit permission to take a picture of this slide when I show you the big reveal. I also have a QR code to the book chapter in which I explain this in much greater detail. So the QR code will take you to the link to the paper listed at the bottom. But what we see is this relationship of an R of 0.3 to 0.6 between liking and intake. But lo and behold, if we look more closely, we see that this is a wildly heteroscedastic relationship. And this is really, really important because what it means is when liking is low, people will not eat it. If it is gross, you don't eat it. However, what if you like it very, very much? If you like it very, very much, you may eat it, but you may not eat it. Just because you like something doesn't mean you eat it. I do not drink a big Cabernet and eat a porterhouse steak every night. Okay? There are many reasons that people make food choices that have absolutely nothing to do with liking. Okay, so then if we look at some data that Case DeGraff analyzed when he was on his sabbatical at the Natick Labs with Herb Meiselman and Armin Cardello and all those guys, on the bottom we see the 9-point hedonic scale going from left to right of a 1 all the way up to a 9, and these are U.S. Army soldiers eating rations in the field, and they recorded from hundreds or even thousands of soldiers how much of each ration they ate. And what you can see is once you give above a 5 on a 9-point hedonic scale, so that's above neutral, you don't really eat more. That curve completely flattens out. A 6 does not mean that you eat more or less than a 9. Now, where this gets even more interesting is they also track, because these were specific military rations with menus where they were offered again, then they said, okay, the next time you were offered that entree, how likely were you to take it? And what we find is even if you rate it as a 9 on a 9-point hedonic scale, so it's you like it extremely, you still are only likely to pick it 50% of the time. So again, this reinforces this idea that liking does not necessarily drive intake. And Kathleen Keller and I have shown the exact same thing using data from her lab in kids. So this isn't just something about Army recruits. So the take-home message here is that people do not eat what they like, rather they don't eat what they don't like. Okay, so I also, while I'm exploding myths for you, I want to tell you the bliss point is a myth. So in 1974, Howard Moskowitz published this infamous paper in Science that gave rise to the myth of the bliss point. Of course, it was built on much earlier work from Bebe Center in the 1930s that Moskowitz was aware of, because that had been done at Harvard as well. But even Wundt wrote about this, and Fofman wrote about Wundt's curve. And so this is a very, very old idea. And in fact, in my own dissertation data, again, we see what looks like this inverted U. However, we have to be skeptical of our own data, because if we do some calculus and solve those quadratic equations, we can calculate a single point that maximizes that function, right? Thinking like a chemical engineer, we can maximize that relationship. However, when we do that, that ignores something critical, which is what is the spread around that maximal value. And in fact, that's what we can see here, that we have a massive change in sucrose. We can go from 5% sucrose to 20% sucrose in this, and liking does not change. So in other words, the bliss point is not a bliss point. It's much more of a big flat plateau. It's a region of acceptability, but it is not a single point that's optimum, okay? And so, in fact, if we look even farther, coming back to our coffee milk sample, we'll find that there's an asymmetrical relationship between the penalty of being not sweet enough and being too sweet. And so we can see that here, that if I'm not sweet enough, I take a big penalty, but if I'm too sweet, then I actually have very little penalty. And so what that tells us is the inverted U is not an inverted U, it's a shallow inverted J, where there's a large flat region. Or coming back to our example of a topographic map, this is like hiking up the hill and then getting to the top of the hill and then picking where you're going to take your picnic on the big flat surface on the top of the hill. And so there's plenty of room where you can move around on that flat surface on the top of the hill once you've climbed that hill. And then to further complicate things even more, not everybody's the same. Individual differences are real. Here's very old data from Rosemary Pangborn and colleagues that was collected in a multi-laboratory study all over the world. And this is where we get the original idea of the sucrose likers, sucrose dislikers, the indifferent people, and so on. And in this exact paper, Rosemary Pangborn warns us that the inverted U is an artifact of averaging across people, and that it doesn't actually reflect the reality for any one person in that data set. And so that has been in the literature for decades warning us of that idea. So when you think of the bliss point, you have to remember that after Howard Moskowitz left academia, he started a consulting company called Moskowitz Jacobs in White Plains, where he was selling his services to food companies. He had to get a hook to convince them to buy his services. And that's what the bliss point is. When it comes to the inverted U, we also see this in the sweet liker disliker phenomena that has been repeated. Here we see this with US data, we see it with UK data, remarkably robust. Some people like more sweetness, some people show that very shallow inverted J, and some people show that disliking curve. But over on the right-hand side of the plot, I'm showing you data that's much less commonly seen, but these are blind taste tests collected in my lab, where we brought 100 people in, and we did 2 alternative forced choice tests, where we made fat at milk at a bunch of different fat levels. And you can see on average in a blind taste test, the red line there, most people like the whole fat more than they like the skim milk sample, averaged across everybody. But if we then segment people, we actually asked them a very important question. We said, if taste was the only thing you picked on, cost, convenience, health, none of that stuff mattered. If you just picked on taste, which would you prefer to pick? There's people that say, I would prefer to drink skim, people that said I'd prefer to drink whole, etc. And then when we plot those same data based on people's own self-identified segmentation, what we find is those dark blue squares, that about 1/5 of our sample really, really does love whole milk. Those are those diehards. They might be compromising to 2% to get their fat intake down, but they like whole milk. But what we also see is those light blue squares on the bottom, those are the people that hate fat. These people in a blind taste test would actually rather have the skim milk than the whole milk. So again, this idea that everyone is maximizing their fat intake doesn't match lived reality. So the take-home message here is that palatability depends on the person, not on the food. Palatability is a function of the person, not the food, and the context. So here's another study that we did where we were trying to take fat out of ice cream while keeping consumer acceptability high. And so what we can see here is that ice cream is a constrained mixture design. And when I say that, what I mean is when you take one ingredient out, if you just take that one ingredient out, the ratio of all the other ingredients is off, and then the ice crystals won't form, it won't be creamy, all these other problems. So you have to add something back in to make up that mass. The same thing is true with chocolate. Chocolate's 54% sucrose, so that's why stevia chocolate doesn't work, because if you take the sucrose out of chocolate, then you end up with something that's just a block of cocoa fat. And so we replaced the maltodextrin, we replaced the fat with maltodextrin, so we cut the amount of fat in half, more than in half. And so for a 3-scoop serving, this would be about a 50 kcal reduction. Or for those of you that prefer to think in watt hours, that's enough energy to run your MacBook Pro for 3 hours. Okay, so that is the energy reduction that we achieved in a regular serving of ice cream here. I know that may not be what USDA says you should eat, but let's be honest, how many people just have 1 scoop of ice cream? And so when we go and we look at this, what we find is that there's absolutely no difference in liking across all those, even though we've taken more than half of the fat out. And in fact, we have no gross differences in texture, no differences in creaminess, no differences in smoothness across this. But then I am a psychophysicist, so we actually did triangle tests, and we did a signal detection theory, and we compared 6% to 8%, 8% to 10%, 10% to 12%, 12% to 14%, 6% to 10%, and 12% to 8%. And so what we find is that a 2-point difference in fat people can't tell. You will notice there is that one red circle there that people could tell the difference between 12 and 14%. However, there's a flaw in our experimental design. We weren't actually testing here whether people could tell a 12 to 14% chance in fat. We're actually testing whether or not people can test the presence or absence of maltodextrin. So they're actually cueing on the presence of maltodextrin, which is why they can do that triangle test. And in fact, lo and behold, that is what we see, that the one that's the highest fat with no maltodextrin is the least creamy and is the least smooth. So the maltodextrin is actually improving the texture when we take the fat out. And of course, this mirrors what Adam Dranowski told us literally 40 years ago, and has at least 5 different papers showing us that people are shockingly indifferent to changes in fat level. People cannot really tell if something's high fat or low fat. Okay, so let's move on to some new unpublished data. So New Pham is a terminal master's student in our department who's working on ice cream formulation. And she recruited 148 consumers to come do a blind taste test. Now, when you manufacture ice cream, for any of you that ever churned ice cream at home, what you're doing is you're actually whipping air into that ice cream. And when you whip that air into that ice cream, what happens is you are creating air bubbles that then set up when you put it into the ice cream into the hardening room, and those air bubbles are what give ice cream its wonderful texture. And so the technical term for that air is called overrun. That's the amount of air you've whipped in. And so a premium ice cream like Haagen-Dazs or Ben & Jerry's, that'll be around like 20-30% overrun, where like regular grocery store ice cream, that would be more like 50-70% overrun. Once you get up to like 120, it does get a little weird. But so I asked New to calculate the energy densities for these. Critically, the energy density is not based on the weight because more air doesn't weigh more. So I had her do it on terms of a 4-ounce serving. And what we can see is that the ice cream at the bottom has almost 200 kcal, and the ice cream at the top has only 100 kcal. So we've cut the total energy in this ice cream serving almost in half, and yet when we ask people about liking in a blind taste test, there's no meaningful difference in ice cream. And then I'm always skeptical, so let's replicate it. So I said, do it again. This time we'll add an emulsifier, just in case that has something to do with the structure or the When ice cream freezes, the fat globules coalesce, so we had to have some emulsifier in there. And we did it with 109 people, and again, we saw absolutely no difference. And it's blinking at me, so I will wrap this up, which is also to point out, though, that if we look very closely, it's not a statistical difference, but you can even see the more dense ice cream, there's actually more people down here that don't like it. These are people that are disliking the one that's more dense and has higher energy. Okay, so clearly intake of high-fat, salt, sugar foods is a problem. I'm not debating that at all. We've known this for decades. Here's British data from the same dietary records you saw earlier, but notice the citation year, that's 1998. So this is a problem we've been well aware of for a long, long time. But I want to tell you, the last part of my story is about eating rate, because in our lab, we found that the mean time to eat one Dorito is 13 seconds, which means if you give people a big oversized plate of Doritos, they can eat 200 kcals in 3 minutes, right? So you can just absolutely eat a lot of energy very, very, very quickly. And of course, I'm employed by Penn State, so I'm contractually obligated to mention energy density in any talk that I give. And so if we think about energy density times eating rate, we can get this measure of flux, or kcals per minute. And lo and behold, when we look at that, what we see is if you use classifications like ultra-processing, unprocessed foods versus processed foods and ultra-processed foods, yes, you will eat more kcals per minute for an ultra-processed food. However, the reason that a box and whisker plot is not a good way to show these data are the fact that this greatly loses all the nuance and it flattens all the nuance that we find when we actually look at the massive heterogeneity of each of those, because if you look at the exact same data plotted as a histogram, that's what it looks like. So there are UPFs that people eat very, very slowly in terms of energy intake per minute. There's UPFs that people eat very quickly in terms of energy per minute, but there's also unprocessed foods that show the exact same thing. So to be provocative here, I'm intentionally being inflammatory. It's not the amount of processing that's the problem. It's not the number or type of ingredients that are the problem. It's not the combination of the ingredients that's the problem. Rather, we unintentionally throw the baby out with the bathwater when we misspecify the problem. Or as we literally heard 2 hours ago, I loved it so much I had to write it down. Our account of causality matters, especially for design of intervention and policy. Because when we misspecify the problem, we take valuable tools off the table. And I know it's really blinking at me, so here's a project we did, taking sugar out of chocolate milk. And what we were able to do is we were able to cut the amount of sugar in chocolate milk using one of these massive fractional fractorial lattice designs again. And we can get equal liking for the chocolate milk where we've taken half of the sugar out. And how do we do that? By adding vanillin back. So when you vilify an artificial ingredient like vanillin, you reduce your ability to do things like meaningful sugar reduction. So it's all about the flavor, right? These 2 pots of butter chicken have identical macronutrient composition. Some of you love cilantro, some of you hate cilantro. These are not equally palatable. So with that, I will answer any questions.
So, the industry doesn't care what we eat, they just want to sell us something. If it's, like trans fat was easy, and we got rid of it in the US because they could substitute it so rapidly with saturated fat and they want to change the products, and they could have a nutritional win. Like, why is the industry selling us high fat, high sugar foods if they can just reformulate it and make them healthier?
Because capitalism. No, seriously, no. You give the food industry too much credit. The food industry is not that smart. They are not able to engineer these addictive products. Instead, what happens is new products are introduced every single year. Most of those new products fail. Rinse, repeat that cycle for 40 years, and the products that succeed and stay on the market due to Darwinian capitalist forces are the ones that are the most delicious and sell the most well. The food industry tries to introduce low salt, low sugar, low fat products, and people don't buy them. Consider the example of artificial colors. When Fruit Loops took all the artificial colors out and went to natural colors, they became very muted. Consumers revolted, and they actually had to reintroduce the OG artificial color Fruit Loops back onto the market. So now there was a period of time you could literally buy both. So the food industry tries to do this and fails because consumers don't buy them.
Thank you.